Thanks.
Or send it to me by email. And I'll like, it'll be easier for me to see exactly by email. Let's see, iPad via cable. Sure. Yeah, can you see it? Yeah, I think it is. Alrighty. Okay, so we're going to start with a tutorial, as I just told you. And today's tutorial is going to be about Feynman diagrams. Now, it's mainly repetition and of things we already said. You know, if we had a tutor, then normally this is a material that basically, you know, there is some overlap with the things we said in class. And if there was a tutor, this is a material that a tutor will teach you. But because we don't have a tutor, I am also the tutor of this class. Then I am teaching you that as well. But I'm trying to do it somewhat even slower than what we go in class to make sure that this is clear to everybody. I don't think we said very many difficult things so far, not too many technical things, except from the last lecture possibly. But, you know, I do want to make sure that it's clear to everybody. So if there is somebody that is not clear to him, then, you know, this is the time. Okay, so the tutorial is about Feynman diagrams. So as we said, Feynman diagrams are really important tools in particle physics. And they really help us to visualize and understand the basic processes that occur as part of the standard model. So this is a great visualization tool. But I'm doing it misjust when I say it's a visualization tool, because it's not just a visualization. It's you learn it more properly when you do quantum field theory. It's a whole concept which ends up with a very nice diagram. And I already told you that behind these nicely looking diagrams, there are very nasty integrals and a lot of thought that gets into these integrals and how to get them. We're actually going to learn the Feynman rules in the coming lecture, but right now we're still just introducing them. What they really help us is to calculate the probability of any relativistic scattering process. Because for that, we need to find the Lorentz invariant scattering amplitude. And the scattering amplitude essentially is what connects the initial state and the final state. Now, the correct way to think of it, right, is that you start with an initial state, right? So you have a particle or, you know, a system which is described by some initial state. And then there is something happens to this system, namely the Hamiltonian is time dependent, right? And as a result, it ends up with a final state. And what happens in between is everything is captured in this scattering amplitude, M or MFI. Sometimes it's called TFI, the transition amplitude matrix. Depends on which textbook you're looking at. So without getting into the details, that's I'm still hesitating whether I should show you the derivation of the Fermi's golden rule or not, because the derivation that you're supposed to study is for the non-relativistic case. That's what you learn in quantum mechanics. So the way to think of it again is you have an initial state. There is an Hamiltonian, which is time dependent. So there is some interaction, and then there is a final state. And the matrix element, this MFI, is basically captures all of that. So it helps us calculating calculate the probability for a relativistic. Putting relativistic because it's also true for non-relativistic, but of course it's true also in the relativistic case. For relativistic scattering process, we need to find the Lorentz invariant scattering amplitude. Is the M. Right, now Feynman diagrams, these are really graphical representation that gives some pictorial description of a way for the system to evolve from the initial state, psi I, and propagate into the final state, psi F. Right, so Feynman diagrams are graphs that give a pictorial description of ways for the state psi I to propagate into state psi F. Right. Now, the full expression for this scattering amplitude is really obtained using perturbation theory. So each diagram represents a contribution to the scattering amplitude, which essentially is translated into a complex number. Right, so the full expression of M or MFI is obtained using perturbation theory. As I said in the class, what we really have to do is to sum up over infinite number of Feynman diagrams. So fortunately, we don't really have to sum over infinite number because the contribution of most of them is going to be negligible under the appropriate conditions, which really saves us. Each diagram represents a contribution. Right. And essentially, it gives us some complex number. Right. After we apply Feynman rules, which I'm going to teach you shortly, it will give us some complex number, which we will use to calculate what we're interested in, which is this cross section or the decay rate or the lifetime of the particle. And translates into a complex number. Okay, now again, unfortunately, in this course, I'm not going to give you the full calculation of how to calculate it using Feynman diagrams, but even without it, I will explain to you how to use the Feynman diagrams, and you know, that's going to be of a great use in analyzing possible interactions that can occur. So let's start with the simplest, a very simple expression, right? So consider a quark-antiquark scattering, right? Q plus Q bar goes to Q plus Q bar, right? This is an electromagnetic scattering between a quark and an antiquark. Right. So the picture we have a quark. It's an arrow propagating, right? It's Q. Anti-quark, the arrow would propagate in the opposite direction. They interact electromagnetically, producing a photon, and then end up with a quark and an anti-quark. Again, this is a small cartoon, right, which represents a scattering process. Scattering process, of course, happens in nature. And the cartoon is just a way to visualize it. Again, time flows in this direction. So this is the incoming particles, right? Psi I. This is the outgoing particles, psi f. Right, so the external lines are the initial and final states. That's true for any Feynman diagram, of course. Right, so left side is the initial state particles, right? So to the left we have psi I, and to the right is the final state. It's a convention, of course, but this whole picture is a convention, right? The internal lines are called propagators. So here we have one propagator. This is the photon propagator. So there is a key difference between the internal and external lines, right? The propagators and the external lines. And the key difference is that the external lines represent true particles, right? Initial state and final state particles, right? So each such line can be associated with a well-defined form momentum. When I say well-defined, I mean a measurable. This is a quantity that we can measure in lab, right? So external line lines, they represent initial, left, and final, right, states of particles. Each such line can be associated with a well-defined, namely measurable, for momentum, P mu, Pi mu. Now, as opposed to that, the internal lines, right, these are really for computational purposes. So they represent virtual particles, right? So in some sense, these are intermediate states that happen during the transition from the initial state to the final state, right? So we assign form momentum to them, of course, but we need that for the calculation. But in principle, they can have different mass or different energy than real particles of that kind. Right? So the way to think of it, these are intermediate state in the process in which the initial state, which is a measurable state, transforms into the final state, which is also a measurable state. This is not measurable. Okay, so internal lines. Right, the propagators. Right, represent virtual particles or intermediate states. Right. Now, by the standard notation is to denote the form momentum by q mu, just to help us distinguish them from the p mu, the form momentum of the incoming part and outgoing particles, right? So the form momentum is denoted by q mu, right? However, that's the important thing. We cannot measure it. It cannot be measured. Right? So since these particles exist for very short times before they are destroyed, right? They can have different mass energy than real particles, right? This, of course, in accordance to the uncertainty principle, where delta E times delta T is greater than h bar over 2, and they live a very short lifetime, so they can have any energy in principle, right? Since these particles, let's see something. If I do like that. Very clever. Right. Since these particles exist for very short time, before destroyed, again, it's not clear if you can say that these particles exist at all, right? These are virtual particles. It's a way of carrying the calculation, right? More than anything else. They can have different mass or energy than real particles. Right? In accordance with delta E dot delta T greater than h bar over 2. Right? The uncertainty principle. And this explains, how we can create, for example, in this example here, right? Think of the way we think of it, right? So you have two, quark and antiquark. They interact, they disappear, they cease to exist. Now you have a photon, which leaves for some very short time. And then this photon ceases to exist and creates a new pair of a quark and antiquark, right? So, you could wonder, how can it be that we have a massless photon that creates a pair of massive particles? right? But it can happen because this photon is a virtual photon, so it can have any energy that we want, basically. Right? I'm basically repeating things we already said in the class just to make sure that it's this is the heart of what we're doing here, really. And I have to admit, it's quite confusing. When I learned it, I think I was a bit confused for a while about the difference between real photons and virtual photons. I'm trying to make it less confusing to you. Okay, the vertex. So the vertex, right? Let's look now at the vertex. Right, Q and anti-Q. And here we have a photon. By the way, I have to say, I checked out how to present the particles. Apparently I was confused or I simply forgot because it's been too many years. But I saw that in all standard textbooks, they use the wiggly line like the photon to represent the weak interactions as well. So the W and the Z interactions are also used by weak, by wiggly lines, same as the photons. The dashed line is reserved for the Higgs. That's kind of become standard, or possibly it became standard today. So I don't want to confuse you about that. I just want to follow what is in the standard textbooks. Okay, so the vertex here, which we denote with an E, right? This is the most important ingredient in Feynman diagram. Right? This is where particles are created and annihilated. Right? This is where particles are created or destroyed. Right? That also describes the type of the interaction we have, whether it's electromagnetic, weak, strong, right? Describes the type of interactions. Right. The important, in our picture, one of the most key features of the vertex is that it enforces all the conservation laws, which is relevant for the interaction. So all the quantum numbers that enter the vertex are the same, are equal to the quantum numbers that leave the vertex, right? Momentum, generation, whatever, right? It enforces all the conservation laws relevant for the interaction. Right? Quantum numbers that enter the vertex equal to the quantum numbers that leave the vertex. Let's come out the vertex. So we have full conservation of all the relevant quantum numbers in each vertex. Now, I said that we really have a perturbation theory. So we have an infinite number of Feynman diagrams, which basically, in principle, need to consider, right? But it's a perturbation, so each one has an order. And the order of a diagram is really the number of vertices that it contains, right? So we have perturbation or perturbative process. Means we have an infinite number of Feynman diagrams. And then the order of the diagram is the number of vertices it has. So that's why we normally work with the simple Feynman diagrams, fewer vertices. Now, each vertex gives a factor which is equal to the coupling constant. Here I denoted it by E. Right? But each vertex gives a factor of the coupling constant. Right? It's essentially, this is a dimensionless measure of the strength of the interaction it represents. So, well, in the example we had here, right, we have two electromagnetic vertices, right? One vertex and the second vertex, right? So we have that I do it like that. Woohoo. Oh, can I make it larger? Okay, so for example, right, in this diagram, we have that the matrix element M, what is proportional to E squared, because we have one contribution of E from here and one from here. So M is proportional to E squared. Okay, is everything clear? Yeah? I won't expect much of difficulties. So, okay, in that case, then let's go for a question, right? So let's start with a simple question. So question number one, right? Consider the two diagrams for the scattering of E minus plus E minus, right? So we have two diagrams. One would be E minus coming, E minus going, exchanging a photon, and another E minus coming and E minus going. And this is, of course, an electromagnetic scattering representing scattering between two electrons. But we also have a diagram which has an exchange of two photons. Right. Right. So let's call this diagram number one and this diagram number two. What's the ratio between the contribution to the amplitudes? Yeah, what's the ratio?
For 1, it's e squared.
Yeah.
And for 2, it's e in the power of 4.
Correct. Right. So the ratio, right? M. Answer is right. M. So gamma goes e squared, and M gamma gamma would go as e to the power 4. So the ratio M gamma gamma over M gamma would go as e to the 4, which is how much this is? E squared, sorry. This we discussed in class. Can you give a real number?
Yeah, we can't hear you.
I ask if you can give a real number. We discussed that in class.
Can you hear me?
Yeah, I can hear you.
So I said 1 over 100.
How much did you say?
1 over 137. Oh, yes.
Correct. That is alpha, which is 1 over 137. That is correct. Thank you. So what is the ratio between the probabilities of these processes to occur? And if we look at the lab, right, we make an experiment. What's the probability that we encounter, the configuration number 2 rather than configuration number 1? So I'm not sure I emphasized enough in class, but that's why we do this tutorial for.
About 1 over 20,000.
Right. So the probability of a process is proportional to the square of the amplitude. Right? The probability of a process is proportional. I should write it down. To the square amplitude squares.
Can an experiment actually tell you which one of the two happened?
Not directly. You can get it indirectly, but not directly. No, it will tell you, well, what you will get essentially, right, as we said, what you get essentially is the cross-section, right? Now, when you can make a calculation. I mean, the whole point of this the Feynman diagram is that you can actually make a theoretical calculation of the cross-section of each process, right? And if you make a theoretical calculation which is only based on the diagram number 1, you're going to get a result which is in excellent agreement with the experimental results, but it will deviate at a level of 10 to the minus 4, right? So the second diagram is suppressed by a factor which is alpha squared, which is about 10 to the minus 4. So your theoretical prediction would miss at the level of 10 to the minus 4. Then you have to add up the correction of the second diagram. Now, as I said, this is depending on the energy that you're looking at, really, because again, the coupling constant is not really constant. Okay. Right. The left one is called the leading order diagram. This is called the leading order diagram. The right one is called the next to leading order diagram. Okay, this result basically shows you one of the very strengths of working with Feynman diagrams. I mean, yes, we do have in principle to sum over infinite number of them, but the corrections we're going to get is going to be negligibly small. So when we work in perturbation theory, that it's often sufficient to stick with the leading or next to leading order, right? Now let's look at this was okay, it's one example. Now let's take another example, right? Sometimes, well, often actually, I don't know. There are cases in which there is more than one leading order diagram. There are cases into scattering process that there is more than a single leading order diagram. Right. So for example, right, when we have this QQ bar, when we have the Q plus Q bar scattering, right? Then we have two leading order diagrams, right? One like that we already plotted, right? Q bar, gamma, Q bar. And we also have the alternative, right? Q bar, Q bar. Right, recall that we spoke about that in class. This is called as the S channel. It's called the T channel.
Is there a specific reason they are named like that?
Yes. I'll show you that actually. S is space, T is time, but I'm going to show you that in a second. Well, not in a second, but if not in this, it kind of come up in one of the calculations we're going to do shortly.
No problem. Thanks.
S for space, T for time, basically. That's what you need to remember at the moment. In principle, in quantum mechanics tells that these two diagrams are coherent. So in order to evaluate the total amplitude, we have to sum them, right? In order to evaluate the total amplitude, we must sum them. Well, this is true for all order perturbation theory, right? So basically M, right, is sum over I, which is in order 1 of Mi plus sum over J, which is in order 2 of mj plus some over k, which is order 3 mk plus whatever. Now going back to your question, right? Okay, not yet to your question, right? Let's discuss again the Mandelstam variables. Right. So the difference between these two types of processes are easier to understand if we write down the four momenta, right? We said there is a conservation of the four momenta. So if I look at the first, the S-channel diagram, right? We have here an E and then we have a quark and anti-quark. Right, so let's look at the momenta. So let's call this the four momenta of the external legs are normally denoted with P. So that will be P1 mu, and this will be P2 mu. And then this will be P3 mu and P4 mu, right? And we said that the internal lines, right, we have conservation of momentum in each vertex. So we denote the momentum of the internal line with a Q. So we have a Q mu, but since we have conservation in this vertex, then it must be equal to P1 mu plus P2 mu, right? Because we have conservation of momentum at that vertex. And now we can look at the second diagram, right? Again, we have two incoming particles, the T-channel diagram. So I have two incoming particles, and again, the incoming particles, I denote their incoming momenta by P1 mu and P2 mu, and the outgoing momenta by P3 mu and P4 mu. But again, I have conservation of the momentum at the vertex. So I call the four momenta of the internal particle, right, with a Q mu. But now, what is Q mu? If I look at conservation of momenta at the vertex.
P1 minus P3.
Exactly, this is P1 mu minus P3 mu. Right, because I have conservation at the vertex, at each vertex. Right, so that's the origin of the definition of the Mandelstam variables, right? The S, right, is just a Q squared, right? So this is just a P1 plus P2, I'm omitting the mu, right, squared. And of course, this is also the P3 plus P4 squared. Right, and the T, again, this is also the Q squared of the T-channel diagram. Right, so it's P1 minus P3 squared, which is also P2 minus P4 squared. Right, and we also have the U diagram, which is just an exchange of the, it's a T-channel diagram exchanging with the P3 and P4, which is valid if we have two outgoing identical particles. So this is just the Q squared, P1 minus P4 squared, which is just P2 minus P3 squared. Right. So the point to note is that, just a second, I think I have a typo in my notes. So I just want to fix that. So for the S-channel process, the total amount of energy, what's available for creating new particles, right, is higher than that we have in the T and U channel, which you can clearly see from here. Now the U-channel diagram, as we said in class, is valid only in, or relevant, right? Only if we have a state, the final state, we have indistinguishable particles, right? The U-channel is valid only when we have two indistinguishable particles, indistinguishable particles in the final state. Right, now when we look here, right, we had here a quark and an anti-quark. Quark, anti-quark, quark, anti-quark. Right, quark, anti-quark. Sorry, quark, quark. Anti-quark, anti-quark. So in this example that we have here, right, when we have a T channel, then each vertex connects only a quark and an anti-quark with an anti-quark. So a U channel is not relevant here, right? So here, each vertex connects only Q or anti-quark and anti-quark, right? So there's no such thing as a U channel here. But if we look at the scattering process of two electrons, so if we have, look at E minus goes to E minus and E minus, right? It's a scattering process. Then we must consider both options, right? So if we had here, right, the two T channels for that, so they have a T channel. Right, P1, P2, P3, P4. Q mu is just P1 mu minus P3 mu, right? But since we cannot distinguish between the electron, the upper and the lower one, the outgoing ones, the P3 and P4, right, they can be reversed. So we can have something that looks like that, right? Two electrons coming, right? P1, P2. And then P1 interacts with the P4 electron, and P2 interacts with the P3 electron. Now Q mu is just P1 minus P4, right, which follows from the vertex here. Supposed to follow from the vertex here. So we must have both options.
Can we have all three options in one process?
Well, if you have conservation, if everything is conserved, then yes. You have to have conservation.
So I'm asking, actually, is there a 2-to-2 process with all the three possible? But it seems to me that there isn't, but I'm not sure.
What do you mean?
With S
Okay.
and U channels. It seems to me that U requires them to be the same particle and S requires them to be each other's antiparticle. So
I
it
think
seems to
you're
me
right.
like
I haven't thought of this, so I need to think. On the face of it, it seems like you're right, but I need to think of it a little bit before I can give you a proper answer.
thanks.
Okay, I'll mark it and I'll give an answer to you on Tuesday. I don't have an answer offhand.
Yeah, no problem.
Okay, so another question. So question 2. Right. What are the leading order diagrams, or I should say, draw the leading order diagrams contributing to the following processes? And so if we have E plus E minus goes to E plus E minus. How many leading order diagrams do we have for that? How many leading order diagrams are there for this process?
It's the same as the QQ bar, isn't it?
No.
Do we allow for non-electromagnetic interactions?
Yes. Allow for the weak interactions. So basically, right? So the answer is, somebody wants to give the number?
Or
4. Very good, right? So we have 2 S channels, right? And the 2 because the intermediator can be a gamma, but it also can be a Z boson. Remember, I showed you that this depends on the energy. Now, when the energy gets close to the mass of the Z, then the cross-section rises, because then the contribution from the second diagram becomes important. And of course, we have 2 T-channel diagrams. And one with the gamma and one with the Z. Can you hear me? I hear a little bit of a noise.
We hear you.
Okay, thanks. So we have 4 diagrams total to leading order. What about the process?
Asaf,
Yeah,
can there be W-mediated processes?
no, because the W is charged,
Okay.
right? The Z is neutral and the W is charged. And you have conservation of charge in each vertex. What about E plus and E minus goes to muon? Plus and minus.
Same?
Nope. Why not?
We allow only for S processes.
Very good, right? For the S, there is no problem, right? For the S, it's actually the same, right? E minus, E plus, and then we have with some U minus and U plus. But for the T channel, so we have two such diagrams, right? Gamma and Z. That's channel. But for the T, what's the problem with the T?
The electron cannot magically become a muon. It doesn't work that way.
Exactly. Very good, right? If we had a T channel, like the one we had previously, then we'd have to have a vertex that connects an electron to a muon, right? But this, of course, violates the conservation of leptonic family. Right? If we had something like that,
So in this sense, the weakest conservation is energy momentum because you can break that virtually. You can break that.
no, I don't break this. I don't break this at all.
Well, you can have a virtual particle off mass shell.
Yeah, the virtual particle is off mass shell, but the energy and momentum is conserved. They are determined by the external legs. I have conservation of energy momentum at each vertex. I cannot touch that. It's a conserved quantity. Now, I don't have any particles that can take away one generation and produce other generation, right? There is one exception, which is the W bosons, right? Because these are the only ones that allow flavor exchange. But here, if I were to write something like that, or to draw something like that, right, then I'll have to have a vertex that, somehow transfers the leptonic generation, right, the E to a mu, and that is not allowed. I don't have anything like that, right? So we have violation of lepton family. Right, in each vertex, both here and here. So this is not allowed. The only ones that enable flavor exchange, but then you have to be careful in how you do it, right? These are the W's. So let's give a third example. So question 3, right? Draw the leading order diagram. For the process kaon decays into a pion, neutral pion, plus an electron plus an anti-electron neutrino. And then which quantum numbers are conserved and which not? Okay, then does any of you happen to remember what is the count made of? Something you can find in the PDG webpage, right? The particle data group. Anybody?
Is it
Sorry?
up and anti-strange?
Very, very, very close. But this is a minus count. This is not a positive count. right? Negatively charged count, so it will be an anti-up and a strange. So the count will make of an count minus is an anti-up and a strange. Now, what is pi 0 meson made of?
Up, up, and up, anti-up, and down, anti-down.
That's true. For our purposes, it's going to be an up and anti-up. It's really a superposition of the up, anti-up, and down, anti-down. But in this process, it will simply end up with an up and anti-up. So we have up and up, anti-up and up. So we can draw that like that. So this will be pi 0, right, and the up. So the strange turns into an up, really. How can it be? Right, the only way is to emit W minus. Remember, the strange quark is a down type quark, so it's negatively charged, right? And the up quark is positively charged, right? So you emit a W minus, so charge is conserved, and then the W minus, right, can then decay itself into an electron and an anti-electron muon.
Can you go back to the QQ bar scattering?
Yeah. Why do you want to? You have several times here. Yeah.
So could you have a diagram like that with a Z boson?
Yeah, I could.
So then so electron positron then is the same as a Q anti-Q.
No, I think I could also do it with a gluon.
A virtual gluon.
Of course.
Okay.
But can virtual gluons be described that way? Because you said they are not perturbative.
I could not use that for what do you mean not perturbative? The diagrams would diverge, right? Well, you're right in the sense that I don't have a free quark, right? What I must have is bound quarks. So in that sense, this is not a real scattering event, right? Just for the demonstration purposes here. Okay, now the perturbative just means that I have to take care. If I want to do the calculation, I'll have to do the full, is the coupling constant of the strong interaction is of the order unity, then it's not enough to take the lead in order. It's not going to give me much. Unless I go to very high energies, and then the situation changes. Okay. Okay, so let's go back to the problem we had. So the decay of the kaon. So basically, we had an S quark that was transformed into a U quark, right? And the only way this can happen is via the charged weak interaction, so mediated by the W minus. So the things that are not conserved, right? So the flavor is not conserved. Of course, that's always the case when we have anything involved with a W. Also, the quarks family number is not conserved, right? Because it involves quarks from different generations, right? The S quark is a second generation, right? So quark family number is not conserved. Okay. Further questions? Well, I'm glad I started with the tutorial because it took me more than an hour. It was supposed to be 45 minutes. So I'll post the third problem set today. I'm sorry I'm a little bit slow in grading your return problem sets. The reason is that I had some deadline. And so once the deadline is over, then it will free my time to do that. So my apologies for that. Questions?
I have one question about the second order that you mentioned long ago.
The second order that I mentioned, yes.
So we plotted the EE with two photons. Yes.
Yeah.
So is there also a second order diagram with diagonal photons, diagonal lines, meaning that the first both of them emit like, so the photon that the first one pushes out is only reaches the second one after, sorry.
You mean something like that?
Yes, exactly.
Let's see. I think so. I don't see any reason why there shouldn't be any. I'll have to double check that, but to the best of my knowledge, I don't see a reason why there shouldn't be any.
Okay, thanks.
But let me check it out. This is kind of, you don't see that in standard textbooks, but I don't see any violation of anything right now.
Thanks.
Yeah. Okay, so in the remaining time, so we're going to have a shorter than expected lecture, which is a little bit pity, but okay, it was important for me that we finish with the tutorial. So let's proceed now with the lecture. So remember that last time we spoke about, well, the general description is decays and scatterings. So I introduced to you the Fermi's golden rule. I said we discussed decays. So I had the Fermi golden rules for decay. Right, gamma, right, is S over 2m1, integral of m squared 2 pi to the 4 delta to the 4 p1 minus p2 minus pn, right? When we have particle 1 decaying into particle 2, 3, n, multiplied by pi, some multiplicity from j equal to 2 to n of 2 pi delta pj squared minus mj squared theta ej d4pj divided by 2 pi to the 4. Okay, mj is the masses of the particles. Right, this is the mass. Pj is the form momentum. Ej is of course pj0. S is a statistical factor that takes care of identical particles. If there are no identical particles, it's simply 1. If there are S identical particles, it's 1 over S factorial. And m is the amplitude. It's a matrix element. That's the name m. Again, I'm kind of hesitating if I should give you the derivative of the Fermi's golden rule, because you learn it in the non-relativistic version of it. You learn it in the quantum mechanics course. And in the relativistic version of it, you learn it in the quantum field theory. The non-relativistic is fairly straightforward. I kind of told it to you in the tutorial what happened really. You start with initial state psi I, you end up with a final state, psi f, which is different than psi I. That means that something happened. Something happened, that means that the Hamiltonian was time dependent. So then you must basically look at the psi I, Hamiltonian, psi f, and do this calculation. It exists in every standard textbook of quantum mechanics, really. I'll see if I have time. The problem is that, of course, as usual, we don't have time. So I don't want to oblige myself to do something which I don't have time to, and you're supposed to learn it anyway. Okay, and then we did some manipulation. There's a lot of delta functions here. The 2 pi is a convention. Every time there is a delta function, there is a 2 pi attached to it. And every time we have an integration, so dp, there is 1 over 2 pi. And essentially, they all cancel each other, which is really nice. And if we carry out this integration, and the theta function is ensures that all the outgoing particles' energies are positive, and we can post that in a easier or simpler format that we showed is equal to s over 2 m1 integral m squared 2 pi to the 4 delta to the 4 p1 minus pn times by j from 2 to n 1 over 2 square root of pj squared plus mj squared. And now the integrate over d cube pj over 2 pi cube. And in the specific case of a 2 particle decay, right, if we have 1 particle that decay into 2 plus 3, then we show that gamma is equal, we actually solved that, and we ended up not even having to carry the integration. Then we ended up that gamma is s times p divided by 8 pi m1 squared, m squared, where p depends on the masses, right? It's just 1 over 2 m1. Then we add this long formulation, m1 to the 4 plus m2 to the 4 plus m3 to the 4 minus 2 m1 squared m2 squared minus 2 m1 squared m3 squared minus 2 m2 squared m3 squared. And then I told you basically that for scattering, we want to calculate the cross section, and we end up with a very similar result. Right. Again, sigma is s over 4 square root of p1 at p2 squared minus m1 m2 squared integral of m squared 2 pi to the 4 delta to the 4 p1 plus p2 minus p3 minus pn. Right, so scattering process 1 plus 2 gets to 3 plus 4 plus n. That's multiplied by pi j equals 3 to n 1 over square root 2j squared plus mj squared d cube pj over 2 pi cube. And when we spoke about two-body scatterings, right, then basically that means that we're starting with 2 particles and we're ending up with 2 particles. And we showed that the sigma d omega is 1 over 8 pi squared s m squared divided by e1 plus e2 squared, and then pf over pi. My pf is the magnitude of the outgoing particles momenta, and pi is the magnitude of the incoming particles momenta. Again, in the center of mass frame, of course. Okay, so this was somewhat technical. And that still misses some important feature, which is what the hell is M? How do we calculate M for the relativistic case? Right? And that's what I want to do now in the remaining times that we have. And I told you we're doing it using what's called the Feynman rules in the relativistic case. Right? Again, the word M comes from the matrix element because that's what represents the matrix that transforms from the initial state to the final state. Okay, but one thing I want to say before I'm going to show you how to calculate it is that this amplitude has somewhat strange dimensions. That depends on the number of particles involved. So just to, as a comment, dimension of M. The amplitude M, right, has units that depend on the number of particles involved. Right. So really the number of external lines, external, incoming plus outgoing, right? So if you have n external lines, that would be incoming plus outgoing, right? Then the dimensions of M are those of the momentum raised by the power 4 minus M, right? So M would have the dimension of momentum, which has the same dimension of mass, right, to the power 4 minus M. So in a two-body scattering process, what's the dimension of M?
Nothing. 1.
Okay, it's dimensionless, right? But if we speak about the decay of a particle into two particles, what's the dimension of M? If we have a one particle that decays into two particles.
1?
Yes, that's 1. 4 minus 3 is 1. Right? So dimension of, well, one dimension of momentum, right? One momentum. Okay. So let me now introduce you to the Feynman rules. So the Feynman rules tell us how to calculate this amplitude from the Feynman diagram. Right? So Feynman rules. Okay, so once we know what is M, we can put that in the formulation that we derived for the decay rate or for the cross section, and then we can calculate directly the cross section or the decay rate of the particle, right? So Feynman rules tell us how to calculate the amplitude M given a model. Feynman rules tell us how to calculate M given a model. Again, they really originate from the Lagrangian of the model. Right, so given the Lagrangian, then we can write down the Feynman diagram and use the Feynman rule to get M, and this really represents a physical process. Again, I'm not going to give you the entire story behind it because it's long. That's the only reason. Now, the important thing to remember is that different models have different rules. Now, the rules are very similar between the different models. When I speak about different models, I'm going to introduce you now the rules for a model that doesn't really exist. I'm going to use scalar fields, right? But in reality, we have boson vector fields, vector bosons, right? And the fermions, which have spins. And right now, I'm going to skip this part. So right now, I'm going to introduce you to scalar, the rules for a scalar spinless particles. So something that doesn't really exist. So just write down the different models. Different rules. The rules introduced here. Will represent a real model. Right, so it's not a real model, but again, the rules, as you're going to see, they are very similar. So we may introduce the rules for the real model later on. It's just a little bit more complicated when you're introducing spins. But for a simplified one, right? But for a simplified one. So in our model, in our simplified model, we only have 3 types of particles. So we assume only 3 types of particles. Right. This is in our model, or simplified model. So let's call them A, B, and C. And they have 3 different masses: MA, MB, and MC. Right? They all have spin 0. And of course, each one is its own antiparticle. I don't assume any antiparticles. So I don't need to draw arrows because particles is its own antiparticles. Each particle is its own antiparticle. So we only have one primitive vertex which connects all 3 particles together, right? There is only one primitive vertex that connects all 3 particles. Right? And it looks like that: particle A, particle B, particle C. Right? And let's say that the coupling constant of this vertex is G. Okay. Now we're also assuming that the particle A is the most massive one, right? And it's so massive that its mass is larger than the masses of B and C together. So we can have a decay of particle A into particles B and C. So we assume that MA is greater than MB plus MC. Right? So what we have here can represent the lowest order decay process. Right? We have particle A decayed into particle B plus particle C. Now, of course, this is not the only option. Let's draw a few other options for the decay process, right? Now, this is the first order diagram, so this is the leading order. What will be the order of the decay process of the next order diagrams? What will be the order? Hi guys.
One.
No, this is one. This is order one because we have one vertex. What will be the next order?
Do you include virtual A's and B's and C's?
Of course, if I have next order, they have to be virtual. Well, the next order has to be 3. Because the particle A, we begin with particle A. Again, think of it, psi A, right? And this is psi B plus psi C if you want, right? So the next order diagrams for the decay right? So you can start with an A, right? It could decay into, let's say, a C, a B, but then we have another interaction. So BA, remember, each vertex here can connect only A, B, and C, according to the theory. So you can have something like that, right? You can also have something like A, B, C, and then they reconnect, but it has to form an A because each vertex has an A, B, and C, and that goes into B and C. Or an A that goes into a B, C, and then the C goes into A and B, but then they have to reconnect again to form a C again. Right, or the same with the B, right? A, B, C, A, C, B. So the next leading order diagrams all have to be of the third order. So this is what our theory allows, right? Remember, I define a theory which allows only a single type of vertex, a vertex that connects A, B, and C. All right. Now it does allow scattering, right? This theory, right? So the theory does allow scattering. Right? For example, we can have an A goes into B and B, or AB. So this one would be something like A B, C, A, B, C. Right? Or A plus B goes into A plus B. Here we have two options, right? We have A, C, B, B, A. We have an A, B, C, A, B. Since you're a bit quiet, then I'm not sure that you all follow me what I'm saying, right? Because before I'm even starting to put the Feynman rules, I told you that the Feynman rules are specific for a specific model. Each model or each theory is going to give me is going to end up with a slightly different rules. So I introduced a very specific model or a very specific theory, which is very simplistic. This is not the reality. It does not represent the particles that we know in nature, because the particles that we have here are spinless, and there are only 3 of them. And there is only one way for them to interact. But this, of course, is for demonstration of the Feynman rules, which I think, given the time, I will only specify them on the next lecture, unfortunately. But I wanted to understand what I'm talking about before I'm going to say it, right? So I have a specific theory which allows in this theory only one vertex and only 3 particles. And now I can specify the Feynman rules, and all these particles, again, they have spin 0. Each particle is its own antiparticle, right? And particle A is more massive than the other 2. These are the rules that I set for this model. Okay, now I can specify the Feynman rules for this specific model. And again, these are going to be different than the Feynman rules for the real life, but they're going to be close enough that you'll see when we discuss the Feynman rules for the real life, then you understand the differences. Of course, I'm trying to simplify first before I give you the full rules, which are simply more ugly, more technical. Any questions? Okay, I don't want to give you the rules right now because it will take another 10 minutes and we are already past time, and then I have to give you some examples so that everything will be clear. So overall, I think I'm just going to skip it for the next lecture on Tuesday. Any questions? No, okay, then see you all on Tuesday. I'll post the next problem set, and I'll promise you that you're supposed to hand up your second problem set today, I think. And let's try to keep it like that from here on. All right.
Thank you.
Thank you, guys. So see you again on Tuesday, and have a nice weekend, all of you.
Thank you.
Okay, what do I do? I do stop sharing. I do and stop recording.